All right, calculus fans, here we go. 6.3a, definite integrals and antiderivatives. We got a lot of rules going on in this section, and you know how I feel about that. There are rules to memorize and there are rules to understand. If we can understand it, we really don't have to memorize some things. So let's go through these with what we know about integrals. Order of integration. Now notice the only thing that's changed here, positive turned to negative, and the order of integration changed, which means let's just say b is 1 and a is 4. If I integrate f from 1 to 4, I'm going to get the opposite if I integrate it from 4 back to 1. That might not be one that makes sense at this time, but it's going to make sense before this lesson is done. We'll come back to this guy. Hopefully I don't forget that. This one should make sense though, because we know that integration gives us areas under curves, but in this case, our area under this curve is only from A to A. So just for an instant, we're finding the area. We don't even have a width of our rectangle like we normally do. So there is no width. Therefore, no width times however tall it is going to be an area of 0. Constant multiple. Let's talk back pre-calculus days. We would have said this. Even if I don't know what the graph of f of x looks like, I could say the graph of k times f of x would look just like f of x, except it would be k times as tall. Well, if an integral finds an area for us, a graph that is k times as tall but no wider would be like having a rectangle go from width to height 5 to width to height 15. All that's changing is our height tripling, therefore the area triples as well. So if the graph is k times as tall, otherwise looks the same. Then the area would be k times the area. Okay, so that one makes sense to me. We can just pull the constant out of the integral, but k must be a constant. Okay, likewise we can pull a negative out. Sum and difference formulas. Well, maybe these don't make total sense, but the formulas are exactly what we would hope they would be. If I have an integral of a function plus a function, I can separate that into the integral of the first function plus the integral of the second function. It's sort of like we distribute the integral, distribute the dx. It looks just like that's what's happening here. Likewise, function minus a function, integral of a function minus a function is the integral of the first function minus the integral of the second function. No big deal. Additivity. This one's a little sneakier, but not too bad. If I have the integral from a to b of f, and then I start at b and continue to c and add that on, I basically have just found the integral from a to c. Well, let's look at it from an area perspective. Let's say this is a and this is b, and clear over here we have c, for instance. Well, the first integral gives me an area. I'm going to call it a1. The second gives me another area. I'm going to call it a2. And a3 would be the sum of those two areas, the area from A to C. So there's another one that makes sense, no big deal. Now this one we have to come back to. This will make no sense to us at all right now, but we will come back to that. Domination, this one should make good sense to us. This says, if the y values of a curve are higher than the y values of another curve on the interval from A to B, so something like curve 1, curve 2, let's say this is A to B, so all of my F, here's F, here's G, if all of these F values are higher along this interval, mustn't the area under this curve be bigger than the area under that curve? Of course it means that. The area under F has to be greater than the area under G. And of course the opposite of that would be true as well. So if f was less than g, then this would be less than that. Okay, now if f is greater than, if f of x, the height is always above 0 on some interval, a to b. So my graph has to be up in here somewhere, above 0, then the area has to be bigger than 0. Again, areas of integrals would be negative if they were down below. They were below the x-axis. So no big deal. So we got to come back to this one, and then we got to come back and touch on this one to try to make some sense out of these. Okay, we did an exercise in class that went something like this. Let's say we have the integral of f of x from 2 to 6 dx. Let's say that's 60. Then I asked, what is the average height of f of x, or the average height of f, I could say. What is the average value of f of x, the average height from 2 to 6? So, I don't know what f of x looks like, but I know between 2 and 6 it has an area of 60. So I'm going to arbitrarily say, well, what if from 2 to 6 we were dealing with a constant function? And now my area in here would be 60. If this is 4, that means 60 minus 4, this must be 15. Now, what if it's not that? Well, if it's not a constant function, maybe it looks something like this from 2 to 6. Mustn't 15 be in here somewhere so that the part, there's my overage, the part above would make up for this part, and we'd still add up to 15. I could chunk away little pieces of this, put it over here, and fill in that area of 60. Okay, so either way, our average height has to be 15. Well, think about it for a second. What are we doing here? We're finding all the heights times all of our little partition widths, multiplying them together. If I divide by 4, 6 minus 2, I've just divided away all of my partitions, and all I'm left with is all of our heights. So our heights would average out to be 15. Then I asked this question. I said, how about integral from a to b f of x dx? We know that equals some value a. Use a just because of area. We say, same question. What is the average height from A to B? Well, let's draw that one in. Let's assume A is a constant. If A is a constant up here, or excuse me, if f of x is a constant, sorry, from A to B, then here's our area we're finding right in here, and we're saying it is equal to A. Well, if I want to find the height right here, how do I get that? How do I get the area? This length from A to B times the height gives me area, so this height must be area divided by that length. Well, what is the length from A to B? I don't know. What would it be if it was 2 to 7? Oh, it would be 5. How did we get that? 7 minus 2, or B minus A. So it's area divided by B minus A is the average height. Okay, now let's go back. Take a look at this. The mean value theorem. If f is integrable on A to B, its average value. Value is our height. That's our f of x. Its average height from A to B is the area divided by B minus A. What am I doing? I'm basically dividing away all of our little dx partitions, and I'm just left with the average height. The height to be being multiplied by that. Okay, hope that makes sense. Now, you may remember back mean value theorem. We had a mean value theorem for derivatives, which basically said if we had a differentiable, if we were differentiable through an interval, smooth, differentiable, continuous, let's say from here to here, what it said was that somewhere on the curve there exists a point that has the same slope as this. So the derivative of this is the same as this slope, or our tangent lines would be parallel. This is pretty similar. If f is continuous on A to B, then at some point, not point C, some point C in A to B, so I got a curve here, my favorite curve, from A to B. We find the average, this is our average height from A to B right here, we just talked about it. if f is continuous and at some point C, somewhere in here at C, we have to be at the average height. In other words, the average height must be contained between here and there. So somewhere in here is our average height. That's all it says. So it's very, very similar to what we were doing before. Now, this is one we're actually going to talk about when we get to 6.4. But now I want to go back to this one. Take a look at number 6. If I were to divide this and this and this by b minus a, I would have min f, we'll make sense out of this, we'll read through it, is less than or equal to 1 on b minus a times integral a to b f of x dx is less than or equal to max, I'm not going to redo this video, max f. Okay, so what that says is on my interval, somewhere on my interval a to b, I've got a min, I've got a max. Well, mustn't, and what is this, remember? This is the average height. So mustn't my minimum be less than or equal to my average height? The average height's got to be somewhere in here. Must it be less than or equal to the average height? And that must in effect be less than or equal to the maximum. Just stands to reason. The only way it could be equal would be if we had a constant function. And now my minimum maximum are the same height as my average. But otherwise, it's strictly less than. So there's one that makes sense to me. In fact, take this one, this one, this one. They're all pretty much in the same ballpark. Okay, and again, we will come back to that. All right, I'm going to get through some of this, and I'm going to wrap this up in a second part. Suppose that f and g are continuous functions, and we've got f from 1 to 2 is -4, integral of. Integral f from 1 to 5 is 6. Integral from 1 to 5, g is 8. What's our integral of g from 2 to 2? Well, they don't tell me up here. But 2 to 2, again, remember, I don't know what g looks like, but from 2 to 2, we have no width of a rectangle, equals 0. Now, what is b from 5 to 1? Well, from 1 to 5, if I reverse that order, and I'm still going to come back and talk about that rule on the first page, but if I reverse the order, I get the opposite. All right. How about 3 times f of x dx? Well, 3 times as tall would produce 3 times the area. I said that exactly how I wanted to. I'm going to say it again. It's so good. 3 times as tall would produce 3 times the area. Well, the area like this. So the area of f from 1 to 2 is given at -4. So this is just 3 times -4 or -12. D is the one that might cause the most problems. F of x from 2 to 5. Well, from 1 to 2, it's -4. So I'm going to try to draw a picture, and I'm going to put it right here. So what I know is from 1 to 2, all or most of the area is below the x-axis because it's negative. But from 1 to 5, which includes 1 to 2, most of it is above 6. So this is a possibility of what f looks like from 1 to 6. Maybe just all of it from 1 to 2 is negative. Doesn't necessarily mean that, but this would be a negative area. And then let's say all of this is our positive. So from 1 to 2, we've got an area of 4 down here. But the integral is -4. From 1 to 5, the integral is 6. If this is treated as a -4, this must be 10. 10 minus the 4 would give us the 6. So our integral from 2 to 5 is 10. We'd actually get it by going 6 minus the opposite of 4. Okay, integral. Well, this would be the same as the integral from 1 to 5 of f of x minus the integral dx minus the integral of 1 to 5 of g of x dx. Well, f is 6 when g is 8. Likewise, this would be 4 times the integral 1 to 5 of f minus the integral 1 to 5 of g. So that's 4 times f. We just had it. F is 6 from 1 to 5. Minus g is 8. So I get 24 minus 8, or 16. Nothing to it. In fact, I'd like to have a whole lot of those on the AP exam. All right, let's find some definite integrals. So how we do that, we're going to find an antiderivative. Definite means they're defined here, 3 to 1. If that wasn't there, it changes things. So we say antiderivative. Well, if I took a derivative and ended up with 7, I must have started with 7x. Now, if this 3 and 1 wasn't here, this is indefinite integrals, we'd put plus c. But with the 3 and the 1, we do this. We put a 3 here, we put a 1 there. And how we resolve this is we put 1 into here. Let's use brackets every time we do this. 1 goes in here, 7 times 1. Then we go minus, put 3 in there. 7 times 3, and we get 7 minus 21, negative 14. Now, imagine if I'd have put 1 here, 3 there. 1 here, 3 there. Then these would be reversed, and I'd get 21 minus 7, positive 14. Now let's go back. BA reversed to AB, they're the same, but they are opposites. So there we go. Can check that one off. I understand that one now. What do I have to remember? I just have to remember this simple little process. Okay, if we took a derivative and got to, forget about the on 8, got to plain old x, x to the first, I must have started with x to the second. But that gives me 2x, and I don't want the 2. But not only do I not want the 2, I also want times 1/8. So this is x squared on 16. Let's take a quick look. 2x on 16, x on 8, from 3 to 5. So I get 5 squared on 16, and that's it for that one, minus 3 squared on 16, which is 25, minus 9, 16 on 16. How about that? Just 1. All right, a little bit more going on C. If I ended up with t to the first, I must have started with, not x, I must have started with t to the second, but t to the second's derivative is 2t to the second, cancel the 2. If I ended up with a minus a constant, then I had minus the constant times x. And I want that from 0 to root 2. I kind of wish this wasn't 0 right here. So we start out, we put root 2 in, and I get root 2 squared on 2 minus root 2 times root 2 minus, I don't know why this is an x, this is a t, I did it twice in that problem, minus, put in 0 and I get 0 squared on 2 minus root 2 times 0, so I get 2 on 2, 1, minus root 2 times root 2, 2, minus 0, or negative 1. Okay, let's take a look at e, my favorite derivative. If I ended with e to the x, I must have started with e to the x. The derivative of e to the x is e to the x. We're running that from 0 to 2. There's a trap coming up here. I get e to the 2, just to the 2, not 2x, minus e to the 0th. Well, e to the second is e to the second, and even though our brains know better, sometimes you see this e to the 0, we think it's 0, but that, of course, is minus 1. D, sneaky. If I ended with 1 on 1 plus x squared, my temptation might be to say ln 1 plus x squared, because the derivative of that is 1 on 1 plus x squared, but then it would be times 2x. And I can rectify the 2. I could divide it out, put a 1/2 in front of here, but that x is going to cause me problems. However, this just happens to be tangent inverse of x's derivative. Sneaky. So this is tangent inverse of x as x goes from -1 to 1. That is tangent inverse of -1 minus tangent inverse of 1. So we ask, when is the tangent -1? Oops, this should be the positive one. Sorry, you knew that. This should be the negative one. When is tangent 1? Well, tangent is 1 at pi on 4. And we ask, when is the tangent negative 1? Well, the place the tangent is negative 1 closest to 0 is right here at negative pi on 4. So minus negative pi on 4, and we get pi on 2. Well, that's a really good time to grab our calculator and say, man, I can't really believe that. Let's get a second. I got to clear this out. And let me get something a little bit more favorable for viewing with the lighting. Okay, so I'm going to go math 9. That is FN int. And I'm going to put in negative 1 to 1. 1 divided by, let's see, 1 plus x squared, all of it, and dx. And I get this guy, and if I take that answer and I multiply it by 2, there's a number that should look pretty familiar to you by the time you're taking calculus. We should recognize that's pi, therefore our answer was half pi, pi on 2. Sure enough. Okay, at this point, I'm going to go ahead and put this on pause. We've got a couple examples that I want to wrap up for you. We've got this guy, and we've got this last one, but I'm out of time for right now. Stay tuned. Thanks for checking in.